Hello everyone. In this presentation, we are going to look at most important instructions, which is called the saturation operation instructions. So for this, we are referring the book Definitive Guide to ARM Cortex-M3 and Cortex-M4 processors. This we are referring chapter 5. In chapter 5, saturation operation is available in 5.6.10 in page number 164. For entire details, you can refer this. The content of this presentation is also referred from this textbook in this particular chapter only. Okay, when we talk about saturation, in 8-bit, 255 is the unsigned saturation upper limit, 127 is the signed saturation upper limit. Similarly, signed numbers and unsigned numbers, we have a saturation limit. So, once the value reaches the saturation, if the processor notifies us, it will be very much useful for us in several applications, purposefully in signal processing applications. Say for example, if there is an amplifier which is amplifying the speech signal, when we talk about speech signal processing, because all are 8-bit or 16-bit or 32-bit processors, for convenience I am referring 8-bit. While amplifying, the 100 value becomes 200. It's convenient. 200 becomes 300 means in an 8-bit the maximum value is only 255. So a register which can hold 255, if the 300 is the value comes means 255 again plus 50 means then 255 plus 1 means it will become 0, and from 0 50 value will come. So instead of 300 it will display as 50 after overflow and something like that. Hope you understand. So in this context, instead of displaying it as 50, it is better to notify it is exceeding the amplification has reached the saturation limit, and by stopping at 255 itself is less disturbance when compared to displaying it as 50 with respect to unsigned saturation. Hope you understood. So this is in analog electronics. With respect, we are calling it as a clipping. In digital electronics, we are talking it as a saturation. So beyond V reference, the signals will get clipped. We cannot amplify beyond the V reference. So the clipping nature in the digital systems is called the saturation operations, where all the multiplication and accumulation instructions and advanced multiplication accumulation instructions are supported by Cortex-M4 architecture, and Cortex-M4 chips are most widely used in signal processing, where speech signal processings are most widely used. In that context, while amplifying, the saturation instructions will help us to notify whether it has reached the upper limit or not, which is more convenient and more comfortable. Okay, so that is what we are going to discuss. Hope you have understood, right? In short, the saturation operation is clipping operation in analog electronics is represented as saturation operation in digital electronics. Here, beyond V reference, the signal cannot be amplified. Similarly, beyond 255, 8-bit cannot represent the numbers. So that is what it is called as clipping. So you'll understand this clearly with the following slides. So saturation operations. When Cortex-M3 processor supports two instructions that provide saturation adjustments of signed and unsigned data. They are signed saturation and unsigned saturation, SSAT and USAT. Cortex-M4 processors also support them, and in addition support instruction for saturated algorithms. Saturation is commonly used in signal processing. For example, after certain operations such as amplification, the amplitude of the signal can exceed the maximum allowed output range. If the value is adjusted by a simple cutting of the MSB bits, resultant signal waveform could be completely distorted. The saturation operation reduces the distortion by forcing the value to the maximum allowed value. This distortion still exists, but the value does not exceed the maximum range by too much, is less noticeable as shown in the figure 5.11. So the signed saturation operation is shown in the figure 5.11. Here you can see signed number means 0, because it is signed means if it is 8-bit means 0 represents 7F, and the maximum value is FF, and minus means it is 80, something like that. So 0 to 7F will be in the above 0 level, and 80 to FF, that is FF to 80 to FF FF to 80 will be in the bottom level. So after amplification, maximum positive number is 7F and the maximum negative number is 80. So when we amplify, if it exceeds that 7F means without saturation, what happens? 7F plus 1, 7F plus 1 will become 80, which is the most positive number will become most negative number as you see here. Because 7F is the maximum positive number in signed 8-bit arithmetic. 7F plus 1 will become 80. 80 is minus 128. So maximum positive number plus 1 will become maximum negative number. And 81, 82, 83, 84 and all it will come like this. So the amplified signal which is supposed to be like this will be amplified like this, which is much distorted signal because it exceeds the saturation limit as we see here. So this is this often this will happen. So to prevent this, the saturation instructions are being used. By using the saturation instruction, this overflow will be prevented and you will be clipping this signal and then it will be notified by the processor where we can reduce the amplification or reducing the gain. So this diagram very clearly explains the impact of the saturation of the digital signal with respect to one-dimensional signal processing, much more clear. For unsigned saturation means 00 to FF, which is the dynamic range. So when it amplifies, it goes below 0 and goes above FF. So with saturation, we can clip those value goes below 0 and we can clip those value goes above. The syntax for signed saturation and unsigned saturation instructions are as follows. Signed saturation, destination register, immediate value, and RN and some shift, which is saturation for signed value. Unsigned saturation, RD, which is destination register, followed by immediate value, RN, and shift, which is saturation for unsigned value, where RN is the input value. Shift is optional shift operation for the input value before saturation. It can be logical shift left or arithmetic shift right. And the immediate is bit position where the saturation is carried out, and destination register is D. Okay, so this is the destination register. The Q bit in the APSR can also be affected by the result. So the Q flag is set if saturation takes place in the operation, and it can be cleared by writing to the APSR. For example, if a 32-bit signed value is to be saturated into a 16-bit signed value, the following instructions can be used. The syntax for SSAT and USAT instructions are as follows. SSAT R1, #16, R0. So for example, signed saturation R1, #16, R0. So let us say the content of R0. Let us say the content of R0 is input, and the syntax according to the syntax if you see, content of R0. The saturation, what is immediate bit position where the saturation is carried out. 16-bit saturation need to be carried out, and the saturated value need to be stored in the destination register. So source register, which bit saturation need to happen, and the result is updated in the destination register. In this context, this is R0 is source, R1 is destination. Saturation was carried out in the 16th bit. Is what you understood from this. So in the table, if you see, R0 contains 0002 0000. So #16. What do you mean by #16? 16th bit is the saturation. That is what you can see. Hash means bit position where the saturation is carried out. So here we have to saturate in the 16th bit. So this is the 16th bit. So the R0 value is here, but saturation should happen in the 16th bit. So the maximum, because it is signed 32 bit, the maximum positive number is 7FFF. So the output is 7FFF. So the output signal is greater than the maximum positive number, hence the Q bit is set. It's very clear. Now here also 8000 is 1 bit greater than the maximum saturation level. So 8000 is minus 32,700. 68. 7FFF is plus 32,767. So minus 32,768 is 8,000 plus 32,767. Instead of showing minus 32,768, it is better to say plus 32,767. There is only one bit error, but here it is total inversion. So that is why saturation is more significant. From the second example, it is much more clear. Okay. So because one bit is greater, hence the Q flag will set. Here R0 is the maximum saturation level. It is in 7FFF, and the output is also 7FFF, and the Q flag will not set. 0 is also a positive number, so the output is also 0, so it is unchanged. This is negative number. FFFF 8000 is a maximum negative number, as we know here, because it is sign extended. 8000 is the maximum negative number in 16-bit arithmetic. So 8000 with sign extended is FFFF 8000 in 32-bit, and there is no change, which is unset. But here if you see FFFF 7FF means 8000 minus 1 is 7FFF. So which has to be replaced as 8000 FFFF, which is the upper saturation limit is 8000. Here also it exceeds the saturation limit, hence Q flag is set. Here FFFE 0000. So because it is FFFF, it is negative number, but it has become exceeded. It has become the positive number. Hence the flag sets and it retains the negative value. So upper saturation is in 16-bit is 32,767, which is represented in hexadecimal as 7FFF. So there is an upper saturation, and there is a 0, and there is a lower saturation, independent of the random variation in the input. The output values are saturated output, and whenever there is an overflow in the input, the Q flag sets and notifies it exceeds the saturation limit in the signed numbers. Table 5.38 with several examples, it is very well understood, and we have understood the significance of the saturation operation in signal processing operations very clearly. Similarly, unsigned saturation is slightly different in that the result is slightly unsigned value. This will provide a saturation operations as shown here, as we have seen right now. And example of a 32-bit signed value to be saturated into a 16-bit unsigned value, the following instructions can be used. The same thing as how we did with signed saturation. So the input is in the first column, which is R0, the output is the second column, which is R1, and the Q bit is this. So here we get this unsigned 16-bit means FFFF is the saturation limit. Here you can see FFFF is the saturation limit and the upper saturation limit, and 0000 is the minus saturation, that is minimum saturation level, as we see here in this diagram. 000 is the minimum saturation level, FFFF is the maximum saturation level with respect to unsigned. So here you can see the output, either it is 0000 or FFFF, and the positive maximum and 0 in between. This is 0, this is 0, and this is 7FF 0, and this is 1, something like that. This 7FF is what with respect to this waveform. 7FF is here, 8000 is here. 1F is 0 with respect to this waveform. 7F is 0 because it is unsigned. 0 to 7F is negative number. 7F to FF is positive number with respect to unsigned in one context with respect to this waveform. So 7F is somewhere here, and 880 is somewhere here. 7000 is 7FF is somewhere here. 8000 is somewhere here, which is within the range. Whenever it exceeds FF, then we have to stop. Whenever it goes below 00, it has to stop and set the Q flag, and then it has to saturate. I look at the examples one by one. The first row, first column, it is 000 to 0000, meaning it is exceeding. There is an overflow because it is 000 and it exceeds, so it is better to keep the upper limit as FFFF. Instead of 20,000, it is better to keep it as 0 FFF, the upper saturation, which is Q flag will set. And here the input is 8000. Here the input is 0x0000 8000. Input is 8000, and the output is also 8000 because it is within the range. And here it is 7FF within the range. Here is 7FF. 00 within the range. 00 within the range. Here there is a negative number FFFF 8000, and because it is FFFF, the minimum limit is 000. Hence it is set as 0. It is 8001, limit is 0. F is minus 1. Minus 1 is not here, so it is 0. So 0 is the minimum value. Hence, it is considered like this. Now you are very clear that unsigned saturation, how the output is visualized in unsigned saturation, and when the Q flag will set, that is also very clear from the table 5.39. Thank you very much.